Hello. In this video, I'll demonstrate the synthetic waveform functions in version 3.12. Insight supports two ways of generating synthetic waveform. One is array-based, and the other one is so-called analytical waveform. And obviously, you can only calculate the analytical waveform when the velocity model is homogeneous. To calculate the synthetic waveform, you go from the processing settings, and you can go first visit the locator tab to make sure you're either selecting a homogeneous velocity model or isotropic layered velocity model. So I'll first select a layered velocity model, and then I'll go to the synthetic waveform tab, and I can see all the options that are available to me. I can choose different wavelet, so either a sine cubic wavelet, the first Gaussian derivative, or the second Gaussian derivative, which actually is a recurve wavelet. Because it's ray-based, so I can calculate upgoing and downgoing head wave as well as reflected wave. If you turn on the radiation pattern, you need to define the orientation of the failure plane in terms of the strike and dip. The rake is the relative displacement across the failure plane. To calculate the analytical waveform, you need to turn the velocity model to a homogeneous velocity model. And then when it comes to the synthetic waveform, you realize there are not much options available. First of all, you can only choose the first Gaussian derivative. You can choose the dominant frequency. And now you realize that empirical moment magnitude is calculated based on that dominant frequency. If you choose a small frequency, then the moment magnitude will be automatically adjusted to reflect a reasonable moment magnitude for that typical frequency. Starting from version 3.12, you don't need events, a real recorded ESF file, to generate the synthetic waveform. You can define the synthetic waveform positions anywhere in the 3D. You access that interface from the array analysis panel, and you will notice this new icon that has been added starting from version 3.12. And in that interface, you typically see the same interface with some additional functions that you can control. You can decide where is the source position. You can either use a user-defined 3D events position if you check that, and it will show location invalid because I haven't defined a user position yet. So I'm going to insert one anywhere in the space, and I come back to synthetic waveform, and now that location becomes available. This is calculating analytical waveform. Because I'm using a homogeneous velocity model, so I need to define the orientation of the strike, the dip, which is the failure plane, and also the failure mechanisms, the relative displacement across the failure plane. The recording time here is the total recording time for your synthetic waveform. If it's traveling a large distance, you want to use a relatively longer time. Particularly for the surface recording, you're probably looking at 1 to 2 seconds. For the borehole recording, it's much less than that. Instead of using a single 3D events location, you can actually define your own 3D positions by a CSV file. If you're familiar with the moment Monte Carlo simulation interface, it's quite similar to the same file structure. So here is the file structures that I used for this demo. The first row is the northeast depth coordinate, and then if you want all of them have different strike, dip, and rake, you can define the strike and dip rake for each synthetic event. If those three columns are missing, then all the events will using the radiation patterns defined here, and they will have the same strike, dip, and rake parameters. And then if I click Start, it will start calculating the analytical waveform, and each waveform are recorded by within 0.2 seconds. So here is the result. The color is displayed by time, so blue is early and red is late. And because I'm starting from the right point all the way to the left point, so there are some differences in time. The strike are pretty much the same. The dip is also in a similar range, as well as the rake. You can choose to display them in DFN disk, DFN plane, or using the Beachbot display. You can also look at their waveforms. For example, I look at the view waveform here, and that's the typical waveforms with that user-defined orientation. That's going to be the waveform looks like. You can choose to display by channel so that you'll be able to see more of the energy. And the P wave energy is rather weak. So it's kind of an indication that you are actually recording on nodal plane or close to the P wave nodal plane. The theoretical arrivals has been picked, so the peaked arrival equals to the theoretical arrival. So if you want to do any processing, you can just directly calculate the source vector and then locate events. And of course, after you do the location, the events will be shifted depending on the location accuracy you required. So this is a very good tool set to evaluate your array. So that's why this function is included in the array analysis module. Thanks for watching.